the rocks inside the earth low, and that's through a process called mantle convection, and it's responsible for everything from plate tectonics, which creates earthquakes and volcanoes near the surface of the earth. It's also responsible for the removal of heat from the deep interior of the earth, which allows us to have a magnetic field generated in the core. But it's all moving around. But rocks they're not glass in the interior of the planet. What we end up learning when we're dealing with sort of materials is that they have different phases. And we're used to phases like solid, liquid, gas, but there are actually a whole lot more phases that materials can have. And it's all about what crystal structures the minerals in the rocks have. And so there are all sorts of different phases of minerals deep inside the planet.
What kind of phases? That's interesting. I've never heard of, I've heard of gas, liquid, plasma, but what does it look like?
So here's the great thing, right? When you have a rock, rocks are made of minerals, and minerals are sort of complicated combinations of molecules. And when you take a molecule, let's take as an example, water, H2O, right? If you take water and you have it liquid on the surface or of the earth, right? You have sort of a typical understanding of what the molecules are doing. But if you take water and you squeeze it really hard, or you make it really cold, then it becomes a solid, but the H2O molecules bond together in a very specific way. Now, if you change the conditions, if you make it even higher pressures or even lower temperatures, the actual crystal structure of the molecules change as well. So there's all sorts of phases of ice, water ice. There's up to like ice 19, I think, right? So there's all different ways that the orientation of the crystal structures can change. The same is true for magnesium silicates, which make up most of the rocks that we're familiar with on the surface of the earth. Their crystal structure inherently changes as they get under higher pressures and temperatures.
So things maybe like van der Waals forces may be radically increased, or hydrogen bonding occurs, or, all different, different kinds of chemistries, right?
Yeah, exactly. It's all about a mineral wanting to be in its lowest energy state given its surrounding environment.
So how do we know what's going on 2,000 miles below the surface? So I don't know if we're using ground penetrating radar, what kinds of spectroscopy or measurements can we do?
Yeah, we do all sorts of different things. And the idea is you use whatever measurement you can and you try and develop a picture. You build a picture from all these different methods. So I'll talk about a few. First of all, seismology has been really important for Earth. We have earthquakes. They create waves that go throughout the planet of the Earth. And the speed of the waves is completely dependent on the material properties so the density of the material and other properties. So we can actually analyze what times these earthquake waves hit different parts of the earth to determine what the material that it traveled through was like. So that's one way. Another way is to use gravity. So we're all used to, if we're doing sort of remembering back to our physics classes and you're doing your problem sets with gravity, you're probably using a value of gravity of like 9.8 meters per second squared or something like that. Right. But the reality is that gravity changes everywhere you walk on the earth, and there are slight variations in gravity. We're talking about very, very tiny bits of a percent of gravity every time you walk around. And it's all about the density, the mass that's right below your feet. So we can look at differences in the gravity as you walk around the surface of the earth to figure out the differences in the masses below you. And that tells you something about what Earth is composed of as well. The last method is my favorite method that I'll talk about is magnetic field. So we have this beautiful magnetic field that surrounds us here on Earth. It shields us from horrible cosmic rays and solar wind particles that are really high energy, cause radiation damage. But this magnetic shield that we have is generated deep inside the planet in the Earth's core. So we can watch how the magnetic field around us changes and use that to infer what's going on deep inside the Earth in the iron core.
How do you know things such as the rocks are rocks instead of being liquid? How can you tell that?
Great question. Turns out that seismology is our friend for this. There are certain types of seismic waves that cannot travel through liquids. So when we see certain seismic waves arrive at different parts of the Earth, we can actually kind of backtrack them and realize what areas of the interior of the Earth are liquid versus solid.
Can you tell the shape of the rocks that are down there, or just that there's rocks?
So what do you mean by shape?
Well, is there a way using any of the spectroscopy to look at the boundaries of individual objects to see the shape or the morphology of the rocks, the size?
Gotcha.
Spherical? Are they jagged? Are they huge? Are they small?
Right. So on the surface of the Earth, we're used to like picking up an individual rock. But what you want to picture in the deep interior of the Earth is you basically just have a sea of rock, right? It's a sea of minerals that are all together. So there aren't these like chunky bits of rock that you can pick up. It's just a sea of minerals, a solid sea of minerals, but it's a sea of minerals. But those minerals can change phase like we talked about before. So you can't really see shape interior. What you can see though is patterns in the seismic waves that tell you about, say, the density of the rocks in certain areas. And in fact, we can see when there are big hot spots in the interior of the earth or big cold spots in the interior of the earth because materials, when they're hotter or colder, change their density. So we can see volcanic plumes coming up from deep, and we can see slabs, which are the parts of the surface of the earth that have subducted into the earth. We can see those reach all the way down to the core mantle boundary.